Hello, everybody. Can we start?
Almost.
Yes. Micro up.
Hello.
Yes.
We have Delphine. Wait.
Yes, she's online.
Okay. Now we have everybody from the jury who is connected.
Perfect.
So welcome to everybody. So I pass the floor to the president of the jury to introduce the defense.
Okay, thank you for the podium. My name is Miloš Pantoš, coming from University in Ljubljana. I'm the president of this committee. Today we have a presentation of PhD thesis entitled Advanced Modeling and Techno-Economic Optimization of Operation Strategies of Electrochemical Storage Systems Accounting for Cycling Constraints. The candidate is Alberto Eric Vazquez Rodriguez. He's going to present the thesis. Let me just introduce the committee. We have reporters, Professor Philippe Poge from University of Corsica. Then we have Professor Delphine Rieu from University of Grenoble Alpes.
Bonjour.
Reporters, yes? Okay, sorry, I thought there is a question. So I will just continue. Then we have Assistant Professor Stefano Baracco from University of Genova, Dr. Theodoros Karlogiannis from University in Brussels, myself, Miloš Pantoš from University in Ljubljana. And then we have, I will just introduce the mentor, Professor Georges Kariniotakis from PCL, and co-mentor, or let's say the chief of this PhD thesis, director of PhD thesis, is Andrea Michiori, also from PSL. Yes, candidate, you got also the reports from Professor Philippe Poge and from, if I see, from Professor Delphine Rieu. So those two are reporters. Other members are examiners for today. Yes, so I propose that you present your thesis in 45 minutes, and after that, we'll just continue with the questions and to the answers. And please provide some stress on your original scientific contributions. So this is one of the main topics, and yes, we are here later again for the questions. So please continue with the presentation. Thank you.
Okay. Thank you, Mr. President, for the introduction, and thank you for the attendees and the members of the jury for your presence today. So today I'm going to defend my thesis entitled Advanced Modeling and Techno-Economic Optimization of Operation Strategies of Electrochemical Storage Systems Accounting for Cycling Constraints. This thesis was conducted at the Research Center per se under the direction of George Kariniotakis, and it was also initially initiated under the direction of Professor François Pascal Nérac. This thesis is done in industrial collaboration with the Nanterre partnership of SPE Industry and the French governmental program CIFRE. So the structure of this presentation is going to be as follows. I'm going to start with the context and objective of the thesis. Then I'm gonna talk about experimental and industrial size setups that we developed and which are key for this work. Afterwards, I'm going to present the battery model development that took place, and And once after that, I'm going to present to you how these models were integrated into optimization frameworks to improve the performance and the behavior. And finally, I'm going to present you the conclusions and perspective of this work. So let's start by talking about RES integration in insular electrical systems. And an insular electrical system is a power system which has no connection to the continental utility grid. What this means is that all the power consumption and production has to be managed and balanced locally, and the grid is more vulnerable because it doesn't have the possibility to make power exchanges with its neighbors. And particularly, I want to focus on the French island of Corsica and the French islands in general, in which, because they have a small capacity of 560 megawatts. And although the island of Corsica does have two interconnections, one with Sardinia, the island of Sardinia, and one with Italy, this interconnection is not to provide energy to the island of Corsica. So for all purposes, it is considered as an insular electrical system. And what is really interesting about the French insular systems is that the BRS penetration is limited to 30% of the total consumption, and this to ensure the grid stability. So once we now have this in head, the natural question that arises is how can we safely increase the presence of BRS on the electrical grid? And what the grid manager can do is to develop solutions to manage the intermittence and to ensure the balance between production and consumption at all times. And to do that, it generally has three kinds of tools, which are power production control, like curtailment, power consumption control, like price signaling to incentivize the consumption, and storage technologies that allow to mitigate intermittence in a very short frame. And one specific solution that we can that is of interest in this work was a combination between power production control and storage technologies, which is the capacity firming. And capacity firming is when we demand from a VRS source a guaranteed power injection for a specific periods of times. So for example, here we have a solar photovoltaic production that has a lot of variability and intermittence. And when we apply the capacity firming framework on it, we can obtain then a guaranteed power during the day, a much more smoother output production. And although deviations can be accepted and can happen, generally speaking, all the energy is going to be there, and the grid manager can plan with that. And to do that, what classically is done is to use energy storage systems. And when we talk about energy storage systems for capacity firming, what we saw is that lithium-ion technologies are particularly well adapted to this application, as they have a very fast response that can work well with the intermittence of BRS. It is easy to scale up or down to meet the specific physical configuration of the power plant that is on site. And also its pricing has been decreasing steadily and is expected to continue to decrease in the future. And so what this has done is that in capacity firming solutions, the lithium-ion based energy storage system have become the common choice to satisfy the energy storage needs of these sites. And now I want to talk specifically also about a specific capacity firming framework that was developed for the French for the French islands and the insular grids, which is the case of a photovoltaic capacity firming framework in 2015. And in this framework, what was established is that newer solar plants were required a minimum amount of energy storage and power. And by doing that, what the grid manager offered was that this power plant was no longer considered as a viable renewable energy source. So the limit that we talked before of 30% does no longer apply to this kind of centrals. And also it proposed a fixed purchase price for the energy with a bonus between 7 p.m. and 9 p.m. And he offers to do all that in this framework for project development, but it also required some strict rules of operation of the sites and the power plants, which were that the engagement had to be done the day before. It established strict limits on the amount of power that can be declared, inject, and furnished to the electrical grid, and particularly also the remuneration and the penalties were evaluated at a per minute basis, and depending on the power injection at each minute and the engagement that was done, the remuneration was calculated, and if there was a very strong deviation, then a penalty for overproduction and a penalty for underproduction could be applied. And so we see that this capacity framework is a complex system, and this complex system needs to be approached in a coordinated manner to offer a system that is fully functional and that answers the needs of this capacity framework. So we can distinguish different steps that need to be considered in a capacity when answering to a capacity framework, which are we need to consider solar forecasting. We need to also be able to model the system and the behavior of the different production systems. We need to be able to generate this engagement that the central power has to make. And afterwards, we also need to make sure that we operate the system in a manner that is coherent with the declaration done before, so we can optimize the operation. And we see that in each one of these steps that needs to be taken into account, there are technical challenges that can be addressed and that can help to optimize and improve the general behavior of the system. And particularly in this work, what we focused was in the modeling of the energy storage system. And afterwards, what we focused after the modeling was the impact these models had on both the optimal engagement and the optimal operation of the plants operating under this capacity framework. So when we focus on the energy storage system behavior, what we saw on the literature was that there was no real models and data that was focused on industrial environments, and that mostly all the models were developed on laboratory conditions. Secondary, these models and the approaches that were available are most often done for single battery cells and battery packs with small capacities. And the case of whole systems and large scale capacities is not fully addressed on the literature. And at last, also another point that was noted was that there is no really knowledge and information on how a specific power application will impact the behavior and the performance of the BSS on time. So having this in mind, we proposed an objective that was to develop a BSS model that was compliant with industrial constraints and that allows the optimization of the storage operation for photovoltaic capacity frameworks. Here, when we talk about the industrial constraints, what we mean is that there's an environment of data scarcity when there are no laboratory testing done, and that the measurements are very dependent on the specific PSS manufacturer and the data that is available, and also that the models need to be compliant with the embedded systems and the needs of industrial sites, so it can be easily adapted and introduced in such systems. So, and to achieve this objective, the methodology followed here was to build several industrial BSS data system collections. Afterwards, with the data collected, we developed a model that estimates several internal states. And with the internal states and the model done, we applied such models in battery scheduling applications, and in particular in optimization frameworks to achieve to determine the best usage of the energy storage. So now let me present you, the experimental industrial sites that we worked upon. So in this work, we built 5 hybrid PV power plants that were developed under the capacity firming framework that I presented just before. And this started with one proof of concept site in the SP facility in continental France. And once the site was built and the separation was validated, an industrialization of the system was done and deployed in the island of Corsica for our client. And what we obtained from these sites at the end were seven BSS that were in operation, from which we can distinguish two different kinds of measurements and two different types of BSS. The type from the experimental site, which is more open in the data available of the battery, and the type seen on the industrial sites, which was a more closed environment and for which measurements are hard to obtain. So when we focus also on the specific behavior that the BSS that the energy storage system has, we saw that when operating under this capacity firming framework, the energy storage have a very specific type of charge and discharge profile. Given the rules of operation, the energy storage is mostly charged during the day when there's an photovoltaic overproduction, and then it is discharged in an almost constant way between 7 p.m. and 9 p.m. So what this does is that the system will have a very recurrent charge and discharge profile that will be charged during the day and discharged during the night for all the days every day during the whole life of the project. So we see that is the BSS will always experience a same type of profile. And the data that we collected from this BSS, what we saw that it was heterogeneous from site to site, given that there was often data loss due to malfunctions, and that the acquisition system that are deployed are less reliable in a sense to gather all the information and save it and save it for later use. And what we obtained was 1.5 years of data from the BSS from the 5 sites, in which we collected the behavior and the different data that was available. And just to focus also on the observability that we had on the BSS, what we obtained was that the two BSS have different real-time values that can be exploited. The experimental site offer AC measurements, DC measurements, and internal temperature, and in addition of indicators of the state of charge and state of health. However, the industrial site only offered the AC power and state of charge and state of health. So that was a difference in data. However, what we saw also is that for both of the systems, the manufacturer provides characteristics of the energy capacity available at the beginning of the life and the charge and discharge efficiency coefficients that in general sense is what we consider as the manufacturer issued model, as this information is what is used in a pre-project development and the study phases. And lastly, another detail that was interesting to see was that the capacity retention of the different BSS can be guaranteed by the BSS manufacturer, but it's also not a standard, it's not a requirement. So what we found is that the industrial site did had a warranty, but the experimental site did not did not have any reference value for the capacity life on time. So after we have a notion of the data that we were able to collect, we focus on the battery model development, and here the objective was to develop a BSS model that answers the need of photovoltaic capacity firming sites, and that is able to be integrated into the energy management system and the power management system. And in here, what we found were several questions about the impact that the temperature can have on the performance on the battery, and how the models that are developed for single cells and battery packs can be adapted and used on large-scale systems that are the data scarce and there is not a lot of information on their behavior. So what we wanted to do for this was we wanted to create a BSS model that estimated 3 internal states: the thermal model, the state of charge, and the state of health. And by determining each one of these, we could at the end have a BSS model that showed the interdependence of the elements. So starting with the thermal model development, the first thing we did was to observe the behavior that the thermal behavior that the storage had when operating under the capacity firming framework of interest. And what we saw is that the temperature of the BSS showed 5 different zones of 5 different zones of temperature of reactions. So the first observation is that we saw that at the beginning of the day there's a temperature decrease that is linked to the heat exchange with the environment. Afterwards, during the middle of the days, we see that there's an increase in temperature that is related to the increase in the ambient temperature, so exchange with the environment, and also the fact that the batteries start to be charged. After that, at night, we start the moment of a strong discharge. So what we see is an increase in temperature. And also we see a small decrease in temperature in the middle of this discharge, which is linked to endothermic reactions that happen inside the battery. But this phenomena is quickly overrode by the ohmic effect and the power that is coming from the battery. So from here, what we obtained concluded from this behavior was that the main factors to determine the internal temperature of the BSS is both the ohmic heat linked to the power that is coming from the system and the external temperature due to the external exchanges. So with this in mind, we approached the thermal modeling, and what we did is determine the internal heat sources, which are the Joule effect, that is the ohmic heat, as we saw before, that is dependent on the state of charge, and the entropy changes that we saw has an impact, but it's a very small one. And also we saw the external heat sources, which are the convection and the thermal radiation. And these heat sources, we parameterized them, we included them in as 2 parameters, which are an internal resistance value and a heat exchange value H, which we use to determine a thermal equation of the battery system. So with this equation, what we did was that we and the data, we estimated the parameters for the BSS studied, and what we found is that the resulting model was able to predict within 2 degrees Celsius the temperature of the BSS will have during the day and at any moment. So this gives us a notion of the internal state of the internal temperature of the BSS is going to have, given the profiles and the specific usage we foresee for one day. And additionally to this, also what we focused was the maximal temperature prediction that we can achieve through this model, given that the temperature can be an indicator to see if we are near a zone of temperatures in which there is some safety concerns for the battery. So what we did is we used the intraday estimation, and we saw the maximal value that it predicted, and we saw that in that case we had a 1.2 degrees error. And another technique that we used was using the scheduled production that is expected from the battery, and via machine learning techniques we determined the maximal temperature that is estimated, and in this case we reduced to we got an error of less than 1 degree for the maximal temperature. So in that way we could not only determine the temperature through the day, but if needed, we can confirm that we won't be reaching a temperature that can endanger the safety of the system. So after the thermal model, we approached the state of charge model. And in this case, but the state of charge is the energy available relative to the current maximal energy capacity. And the classical way to determine it is through the Coulomb integrator approach. And here is written in power form. And this it means that we can calculate a model of the state of charge with just determining one parameter, which is an efficiency coefficient. And this efficiency coefficient is traditionally what the constructor gives about their energy storage. So it is what we call the manufacturer's SOC model when we use the efficiency coefficient furnished by the manufacturer. However, what we saw also is that this simple model is not able to answer the most complex behavior that the state of charge can have for a battery, such as thermal dependence, the thermal dependence of the state of charge. So to alleviate that and to incorporate this dependency, we did an improved approach that added a second parameter that is still dependent on the temperature. And by doing this, we can model part of the phenomena that is related to the internal temperature of the temperature, and it also allows us to coexist and co-estimate with the thermal model done before. So there are systems that can work in parallel and co-estimate one another. And when applying these models and using the when we parameterize these models and we see the results that they give, we see that the average error for a state of charge estimation was reduced from 8 to an average of 3% for all the systems. And when we use the improved approach with the thermal dependence, what we saw is a similar result to the one before, which is resilient. So we can include the thermal dependence, and we don't see a degradation in a state of charge estimation. So we see this state of charge estimation is better, and we try to apply this model on the developed sites in the 4 industrial sites that we built. And we saw that by including this improved parameterized state of charge model, the average error of the state of charge during the operation reduced to 4%. And by association, the general operation of the site improved, and we saw a higher increase in revenue and a decrease in penalties. And in general, this meant a revenue improvement between 1 and 2% per each of the sites in terms of penalty. And at last, we attack the problem of state of health modeling. The state of health, which is the maximal energy capacity the system can hold at the moment relative to the initial maximal capacity. So if a system had a 100 kilowatt hour initial capacity, and now it can only hold 80, then that means that his state of health is only 80%. And when we study the state of health modeling, what we saw is that there are many phenomena that can be at origin of this degradation, and most of them are very chemistry related to the system. And so what we also saw is that given that it's very dependent on the chemistry of the system, the behavior will change given the specific chemistry that is subject on the study. And when we want to model the state of health, there are classically two approaches. One is use calendar aging, which is just the degradation that happens when the battery stays still, and cyclical aging that happens as we are using the battery to charge and discharge and furnish some power. And what we did is we use a model that includes these two phenomena within 3 parameters. One, which is the formation of a solid electrolytic interface on the battery, which is a layer that degrades the performance, and 2 parameters that beta and F, which encapsulate the degradation that the system has due to the calendar aging and the cyclical aging. And this we can do it in a simple manner, because as we saw before, the behavior of the storage and the power profiles that we have is very recurrent, and also is expected to be on a daily basis. So we know that the calendar aging is implicit on the cycle degradation. And one of the feedbacks that we saw from the industrial sites was that the energy available from the deployed sites was higher than the guaranteed value. So we needed a model that was able to reflect this different behavior. And when we parameterized the state of health model for each of the energy systems, what we found was a net reduction of the error when predicting the state of health of the battery. And in general, what we saw was that the warranty provided by the BSS manufacturer was very pessimistic, and is not, in any case, it's not well adapted to the application that we have in hand, as the BRS capacity firming framework at the kind of usage degrades less the system. So once we had the three models, now we could join all the three in the BSS model that we wanted, in which we can estimate each of the internal parameters individually, and if required, we can co-estimate them and make them interplay, and to obtain a generalized BSS model that can be integrated into the system, given the information that is available for each site. And to summarize what we did on the Barry model department, we proposed a temperature estimation model that is able to predict within 2 degrees Celsius the temperature of the energy storage, which gives a real indication of the temperature at which the system is going to operate. We also propose an SOC model that can be trained only with the AC power and the state of charge indicator that is furnished by the BSS. And also we saw that the BSS degradation from the PV capacity firming framework of interest is less aggressive to the energy storage system than the warranted values, and thus we can foresee that the system will operate for longer than the initial study or prevision could have foreseen. And afterwards, once we had the models, we approached the problem of how to use them, and for that we had an objective of building an optimization framework for both photovoltaic and BSS hybrid power plants that allows us to integrate the different BSS models and study the impact that these improved models have when compared to the factory issued values. So here, the question was, what were the impacts from each of the states on a PV capacity framework, and what will be the impact of such model could have when approaching another scenario, such a microgrid with flexibility requirements. So we start this part by defining the optimization problem that we had in mind. So in this case, we have interactions between the solar system, the battery system, and the electrical grid. But because in the capacity firming of interest, all the interactions between the solar and the batteries is done through the grid, we can simplify the system and just consider three power exchanges. And what we did in this scenario was a model for work the constraints that each element can have. So for the grid, what we supposed was that the grid was an infinite energy source and sink for both the solar system and the battery system. So it can absorb all the power from the solar system. It can furnish all the power that the energy that the battery can receive. And additionally, the grid was the point of interest of the optimization problem. So what we wanted to do was to be in coherence with the capacity framework. We wanted to increase the power injection and minimize this power injection hence with a previous scheduled power engagement. And what this does is we get an objective function for the optimization problem that maximizes the power injection and minimize the cost of the difference between the two. For the solar behavior, what we did is we suppose that it can have one of three different behaviors, which are classical solar inputs. One that is very smooth and high energy. One that is a lot of the same and similar in energy, but with a lot of variability, and one that provides not a lot of solar resource and a lot of variability. And from this, we suppose that this could be the input of the solar system, but we also allowed the fact of photovoltaic curtailment. So we could actually use less of the solar energy than the available resource, which translates to these two optimization constraints. And at last, for the energy storage system, we wanted to constrain, of course, to its physical limits in power and in energy. And to do that, we defined the physical limits of the system, but we also included a state of charge and a temperature model for which the specific function can be adapted depending on the model that we want to integrate. And in this, when including the models, what we can see is that by changing the parameters that are available in this model, we can either include the factory issued model, we can include the state of charge model that we propose, and we can also include the state of charge model that with thermal the temperature dependence that we worked upon. So this allows us to integrate any of these three models on the capacity, on the optimization framework. So once we established the basis of the optimization framework, what we saw is that we got two different optimal optimizations that we can do for the PV capacity framework. We can either determine the optimal engagement, for which we can see the different constraints that we spoke before, and in which, given a possible a PV forecast, we determine the best engagement that the system can do, and also we can optimize the production, in which the engagement is considered as an input of the system, so the optimization problem is simpler. And in this case, we obtain the best possible outcome given the previously engagement and the real photovoltaic production can be done. So once we have these two scenarios of optimizations, what we did is we run the process. We use a solar forecasting. We introduce the system modeling. We determine the best production engagement, and then we studied this the impact. We optimize the operation given the engagement. And generally, what we found is that by introducing our proposed SOC model, the revenue estimation for the optimal operation decreased almost systematically for the four systems. And what this tells us is more than if we use the manufacturer issued BSS model, we're going to have results that indeed are going to be higher possible revenue, but these are revenues that is going to be impossible to attain. So by using an SOC, our proposed SOC model, we get less revenue, but there are realistic outcomes for the system. And using the same base of this optimization framework, we also treated the subject of a microgrid scenario in which it was a low voltage network, and similar to the one before, we had a battery system, but now instead of one VSS, we talk about 3 individually controllable PSS. So what it does is that it adds extra complexity to the problem and adds a battery aggregation problem into the mix in this optimization framework. Secondly, we define a local load that is now the objective. The objective function is the thing that the optimization problem needs to be able to supply. And as a consequence of that, as there's a local load to satisfy, what we did is that the electrical grid is no longer, is still an infinite energy source and sink, but no longer is incentivizing injection, and instead it is penalized. And because the grid is a separate element, we could determine a specific injection at any moment, or we could ask for it a specific injection at any moment, which can add a flexibility requirement to the operation of this microgrid. So when we did the microgrid scenario, the results without any flexibility requirement, we saw that using the improved models, just as in the case of the capacity firming framework, the cost of the energy, the cost to satisfy the local load increased in both cases, with and without the thermal dependency and the state of charge model. And also, when we included the flexibility requirement of a specific power injection for a period of time, and when we included the deviation from this requirement as a penalty, we added a penalty for that. What we saw was also that adding the improved SOC and the SOC model with thermal dependence increased the overall cost by 2%, reaching up to global 10% when considering flexibility for a system. In this case, what we saw is the thermal consideration does not significantly changes the cost to satisfy the flexibility requirements, so it has a minor role. And although another thing that a last insight from this part was that the degradation expected from the 3 BSS when using the improved SOC model is less than when using the manufacturer model. However, this decrease in degradation does not compensate the 2% increase in total energy cost to satisfy this grid. And in conclusion, what we saw in this optimization framework, and the summary was that we propose an optimal scheduling and operation optimization framework that was specific for the PV capacity framework of the ALSDNI for the capacity framework of interest, and that we saw that the proposed SOC model showed in general a worse expected revenue, but which is more realistic, which can help to better determine the financial results of our newer projects. And also in the microgrid scenario, what we did was we included 3 BSS to satisfy a local load, and we saw that just as with the scenario, the case before, the inclusion of the proposed SOC models increased the overall cost of running a grid. And to summarize with the conclusions as perspective of this thesis, what we did in this thesis was to develop a LibES model that, given data sets from real in-situ industrial sites, we adapted the BSS models to this data. So it is ready to be applied in other similar industrial sites. So we obtained and collected data regarding this BSS, and we developed a libes model for different internal state parameters estimations, and we found that we improved the error expected from such, and that we can apply to other applications. We also integrated the BSS models done before into the capacity firming and then microgrid optimization frameworks to evaluate its results, showing generally how using only the manufacturer model can give to erroneous assumptions of the revenue. And at last, we also evaluated the benefits of the state of charge and thermal component co-estimation, which can be very subtle, can be very subtle, and so it's very depending on the application if this increase in the co-estimation and temperature value is required. And regarding the perspectives for other works, with all what we've seen, there are clues that to use to determine the different use case and different application scenarios in which the inclusion of the thermal component can have a more important impact on the operation of the system. And so a research on these scenarios and that benefit from this can be of interest. We could also foresee a clue in for the state of health modeling, in which we include seasonal capacity loss due to the ambient temperature, relative capacity loss that will be that is reported as loss, but given when the temperature rises, it will be recovered. We can also foresee the integration of the BSS models into optimization and to stochastic optimization paradigms, so that we can evaluate how these models impact the optimal operation given the variability of the production. And also we can also envision some works on the integration of the capacity degradation onto the optimization problem itself. In this work, it was more an observed variable, but we could foresee also the optimization problems that are aware of this degradation and optimize it accordingly. And at last, we could also see how these works could finish onto studies to determine the best capacity and the best BSS to apply, depending on the geographical locations and the external temperatures that are expected to have on such sites. Thank you very much.
Thank you for your nice presentation. It's very interesting. Okay, now we'll continue with the questions. First of all, at the beginning, I will give the podium to our reporters to comment the work and also to express some questions. So the first one, Professor Delphine Rieu, floor is yours for the questions.
Okay. Thank you, Mr. President. Thank you, George, for your invitation. And of course, thank you and congratulations, Alberto, for your presentation, the dynamic of your defense, which present the key points and the main contribution to the state of the art. Is it okay for you hear me?
Yes, I hear you. Yes.
Okay. So, of course, yes, I spent time to read the report, but I have some questions for after the defense. So maybe I can start with general questions. The first one concerns the models.
Yes.
Because as you said, the model of the battery is dedicated to the application of PV installation. Okay, and I wonder what will be the great difference of the model if it is used in another application. In fact, do you think that the model is very specific to PV system, or could you use it in another framework, for instance, in association with wind farms or directly in connection with the grid?
Yes. Thank you for the question. Yes, indeed, the model itself with the parameterized values, yes, they're going to be very tied to the specific application. However, because we focus more on the kind of industrial system that we have, we prioritize the fact of using widely available information. For example, for the state of charge, there is only two data that is. Two informations are required. So as for Aeolian applications, for instance, if energy storage systems are applied, they will have a very similar data that will be available. So the models technically can be applied on those. Instead, the behavior we expect will be different because here it was tailored to the specific curves we saw. But generally speaking, it will be the same process to achieve to adapt to another specific power application.
Mm-hmm. And in fact, I think that the method to build and to make a parameterization of the model is very general. And so I think, from my point of view, that you should maybe publish a little bit more about the model. I think it could be very interesting for many engineers and researchers to understand the way you make the parameterization of such a model using a real case, in fact. So I think the model is more general than you said, in fact. Well, it's my point of view. Maybe another general question. Finally, what are the main limits of the study?
What are the main limits of this study?
Yes, from a scientific point of view, of course, not from an industrial point of view.
Sorry, I didn't understand the last part.
I think about the scientific limits, not the industrial limit associated to your work.
Yes. So about the limits, what we can see is that actually we are very quickly limited to the kind of ESS that we have at hand. So if we wanted to really expose the application of this and see its coherence in a scientific sense, we will also need to test it in many more energy storage systems. So that can be a limit that we find ourselves that in a more broad generalization, this is not these models do not follow, do not behave as expected, and also the optimization problems can become very cumbersome. So we can also face a technical limit on the amount of scenarios that we can introduce the BSS models, and in which we can no longer extract any more useful information or for other applications.
Okay, thank you. Maybe a last general question. In the first chapter, you propose a very large state-of-the-art, which, from my point of view, is really complete about the other works from others, researchers. But maybe just a question about the local state-of-the-art. It means when you begin your PhD, what was the state of the art of the team, the lab, and so on?
The state of the art of the team. In here, there were already works that were done on optimization, but it was more the works that were done in the laboratory were more around the best schedule possible given the systems, but the subject of the Barry model itself was not really the point of focus. It was considered as an element more, and the system regarded the works were more around around the interactions between them and how to schedule them correctly.
Okay.
I don't know if I answered your question.
Okay, and
It's
about the collaboration with SPI, it was the first work with this company or not?
I think it was. I'm 100% sure, but I think it was the first thesis that was done in collaboration with SPI. Since then, we've had SPI has had two or more PhD candidates, but I think it was one of the first at least.
Okay, you were the first one. Okay.
Yes.
So thank you. I have maybe several technical questions to complete. The first one, if you can come back over the slide number 23.
Yes.
It's about the thermal model, in fact. You have observed a derivation of the estimation with time, which seems to be normal. And I wonder if you have taken into account the fact to make a recalibration of the model according time. It means, do you think it will be interesting? I don't want you to say yes. Do you think it will be interesting to make another estimation according time? It means you observe a derivation with time. Maybe as for the SOC, which is also an estimation, you can stop the system, make a measurement, and so recalibrate the model according time. I'm not sure to be...
Yes, the idea of the models was to reach to a point in which the online measurements are enough to recalibrate and have a general idea of this. For the thermal model, it's not something that we aim to do because we saw that it had for the industrial systems, it was something that did not apply. So no further attention was given to recalibrate. However, because as you said, there are parameters that evolve. The internal resistance increases with the time as the battery starts to degrade. We can expect from these models to evolve and to generate more heat with the time. So there can be an interest to doing that. So far for this capacity firming framework, it wasn't neither a priority because we saw that the expected operation we fall largely within the safety zones. So there is no really particular question that arises in terms of safety of operating on very hot conditions. But in that case, in any case, what we do is we continue to monitor the temperature of the systems, and the day or the moment that we start to see that the temperature surpasses a predefined value, in that case we can say, okay, now the operation of the system has degraded itself to a point where we need to have this information, and we need to be able to adapt our power profile to minimize this scenario. So it's something that indeed can be of interest, but given the specific was not really focused.
Okay.
Yes.
Maybe another question. If I have understood, you didn't, sorry, taken into account the calendar aging in the modeling. So do you think that after 3 or 4 days of shadows or dark days, you could have an impact of the calendar aging on the battery?
Yes, we could have an impact on the calendar aging. However, in our specific scenario, the capacity firming, how it's built, even when there is no solar production,
Yes.
we are expected to charge the batteries during the day. So there will be a cycle.
Okay.
That's what is very particular of this capacity firming framework, is that even if there is no solar production, we are incentivized to charge them and sell them at where there is an energy bonus.
Okay, thank you. Maybe on slide 34, Mr. President, please stop me if I need to control
Okay,
the
maybe.
time. Yes,
Yes,
thank you. 30.
we have time for one question.
30. Not 40, but 30.
44.
44. 34. Sorry.
Yes.
Sorry.
I'm not sure after the reading of your document and after seeing the same slides, to understand finally the key reason for which the manufacturer data are less optimistic than your own measurements. So from your point of view, I apologize if you have already discussed about that, but what is the key point for you for which you are more optimistic than the manufacturer data? Because classically, for my own research works,
Yes.
we have observed exactly the contrary.
So what was the question? So I lost the...
Sorry. Do you try, for instance, to discuss with the manufacturer of battery to understand?
No, we did not have a direct exchange with the manufacturer. After that, what we saw is that generally speaking, our models, our state of charge models, were the performance expected from the BSS was less than the expected performance that the manufacturer had. Is that you have the exact the contrary results in your research? Did I understood that correctly? I'm sorry.
Maybe it's not really this slide, but maybe the 33. I apologize. The 42. Or sorry. Yes, on the plot. If I have understood.
Yes.
The warranty. So it means the data from the manufacturer give a capacity loss upper than yours.
Upper. I lost the last word.
The line with the dot
yes,
line
the warranty, yes.
in green corresponds to the manufacturer data, no?
Yes, that's the manufacturer warranty.
Okay, and so my interpretation is that the model from the company is less optimistic than yours.
Oh, yes, indeed. Yes, I'm so sorry. I got confused with it. Yes, exactly. Yes, what we found was that the warranty of the manufacturer was less optimistic than the real behavior of the system.
Exactly.
Afterwards, we also rationalized this in a sense that due to the warranty having some financial impacts, the manufacturer has an interest in being pessimistic on their warranties, as otherwise they can be financially penalized by the constructors. But yes, what we found is that in any case, under our specific scenario of usage, the degradation is less than the expected.
So it's linked to the usage only for you.
Yes, in this case, we will say that what we understand is that this less degradation is linked to the usage that is more soft, so to use to put a word on it, than the foreseen usage by the manufacturer.
Okay, maybe I have two last questions. It's possible, Mr. President?
I'm not sure if you have time because we have limited time. So
okay.
if you are being very fast, we can do it.
Okay.
But also, yes, the candidate just try to answer as fast as possible.
Okay, but
yes.
I know that Philippe has a lot of questions also. Maybe a question about the EMS. So the optimization. So you have showed that finally for the case study, the use of a very complex model with a thermal link with the calculation of SOC and SOH, it's not so relevant. It means that you have proved that finally the gain for financial estimation of the project is not requires not so many this model, this complexity of the model. It's okay. And I wonder if it could be interesting. You didn't talk about that in the prospect. Is it interesting to maybe think about a reduction of the model, the thermal model complexity?
Yes, indeed, that is something that we could see. The benefit from that was very limited. So indeed, we could foresee an approach in which the thermal model is simpler. We gain still some insight of the behavior, and that way we can further facilitate integration into EMS. Indeed.
Do you have think about the way to reduce the complexity of the model?
The complexity of the thermal model actually hasn't been real. Wasn't reworked after the initial proposition, but it is something that we can work upon and see how we can improve the application on EMS. That's a very interesting point too.
Okay, so maybe if you are interested by such a subject, I propose you to read maybe the works of the team of Mr. Vinassa at Bordeaux, who work on the thermal modeling of lithium-ion batteries, for instance, and for reduction of models, you can find a lot of works in the literacy. So I think you will find some good ideas in this state of the art. Maybe my last question, which is also a general question. So you have worked on the optimization of the cost, of course, thanks to the industrial support of the PhD. But in 2023, it could be interesting also to integrate SDG, so Sustainable Development Goals, in any project of research. So from your point of view, after 3 years dedicated to this subject, what do you think about the sustainability of your solution and how to improve the optimization thanks to sustainability criteria? A very simple question.
Sorry?
A simple question to finish.
Yes, the optimization framework that we did, indeed, we could integrate, in any case, a cost or an incentive to take into account the sustainable goals, and that way we could foresee an optimization problem that spans in a longer time frame to include such kind of behaviors, because otherwise it will be interesting to see how how much does this sustainable goal can impact on a short time frame as 1 day instead of a macro visualization. So that's a point that can be of interest to see.
Yeah, and thanks to the characteristic of the mix of energy for Corsica, for instance. Okay. Okay, thank you very much for the discussion, and thank you, Mr. President.
Yeah, thank you for the questions and for the answers. It was very interesting. Now we'll just continue with Professor Filip Pogi from University of Corsica to ask some questions or just to debate.
Thank you, Mr. President. Firstly, I want to congratulate the Mr. VAZQUEZ for the report, the memory of the PhD memory, and for your defense, which is very, very interesting, clear. And I have some questions. The first one is nearly the first you have from Professor Rioux. It concerns not the sources but the uses. You have made your modelization using a base case of the call tender from the crew. What is the impact if there is another using? For example, the last call tender, it is not the same for the batteries. Has there an impact of your models or parameters?
Yes, indeed. This capacity framing framework, as you said, is very particular, and the last one does not include the same financial rewards. So in any case, for the newer sites, from what I collected for the newer call for tenders, there is less of an incentive to deploy large scale systems. In any case of more than 1 kilowatt hour per kilowatt of installed power, there is less incentive, and therefore the behavior that we can expect from the storage system is going to be more variable and many more cycles. So in that case, I'm not. We could do a similar approach of this optimization problem, but the behavior that we're gonna see from the battery is gonna be crucially different. So it will be needed to study if the parameterized models really adapt to this newer scenario and to this new kind of discharge and charge profile of the system.
Yes, and do you think it's easy to do, or you have to make some huge studies for evaluating the new parameters concerning other cycling?
For the new parameters, what will be needed is just collect some data of the sites, and in theory, to change the optimization problem to adapt to the newer call for tenders is relatively involved, and not involved in the guillemets, easy task, given that there are less constraints on engagement than before. But the model, it will need to reparameterize them with data from the sites to be sure that we can actually say that the expected revenue, given the optimization site, is something that will be near the real revenue. I don't know if I.
Okay, and the other questions, it is for Rox and for my precedent questions. Do you need a large set of data to make your models? For example, 1 week, 2 weeks, or 1 month, 1 year. What is the good step of time to make your validation?
We don't need that many data to parameterize. However, logically the precision of the model will be less and less adaptable to many situations. However, what we saw was that 1 year data is a good starting point, because it was able to collect the behavior under the weather and the conditions, solar condition that we expect from a site in general. But other than that, we can foresee working with 1 month data to parameterize, and that rejoins what Professor Ria said, is that we can readapt or recalculate the newer model with the data to each time improve the value, the performance of the model.
Another question concerns the batteries and the technology of batteries. For your case study, you are using some lithium batteries, LFP, I think. And if it is another technology, do you think it's the same case?
Sorry, I did not understand the question.
Your modelization is dedicated to lithium-ion batteries, okay?
Yes.
And the technology, there are various technologies using your lithium batteries, like LFP, for example. And if it is another technology using your lithium battery, do you think it's the same case, the same compartment?
No, in that case, we can expect a different behavior. Particularly here, what we saw is that thermal dependency was less impactful than foreseen. But on other technologies, we could see that the temperature plays a major role. So that the co-estimation, instead of being an add-on of the temperature, it becomes a necessary value to improve this management. And
in fact, in your studies, we can observe that the temperature is very important to determine the parameters. Yes, it is very interesting. I have another question. Your systems, your modelization concerns your overall system batteries, and you know these batteries are constituted by cells, and how you can imagine to detect the default, for example, for some cells, in view to improve the comportment of the overall systems.
Yes, the battery faults and battery cell faults in the systems for us were more of an embedded in the data. We can detect it because when we see a sudden changes that our model any sudden changes can be related to that. If we have a model, we could also use that model to determine if a sudden change is abnormal, and in that case optimize either the time of to repair this fault for on sites. So that is something that can be but other than that, it is because it's a whole system, we cannot forcibly detect which cell can be is at fault, but however we can see and we can distinguish when something isn't right. I don't know if that's
Okay. And the last question, your modelization, your development have been installed in the solar systems in Corsica?
The models, yes. The state
Yes.
of the state, yes. The state of charge model has been installed on the sites of Corsica. It is used. It is used to determine the schedule of the sites, and however the thermal model is not included, but the degradation of this model was used to foresee the financial repercussions that's going to have as under the contract of these specific sites. There are some financial engagements, And having these models allows us to defend, or in any case have better engagements to make with the final client and the PV developer.
Yes, it was the last question for me. All my congratulations, and thank you very much for representation and answers.
Thank you very much.
Up to you now, President.
Thank you for both of you. So we'll just continue with our examiners. So we finished with our reporters. The first examiner is Assistant Professor. So please take the podium.
I'm gonna cough. I'm sorry. Yeah.
Okay. It's my turn. Yes. Okay.
Yes.
Yes.
So thank you so much for the presentation, and I have some specific questions and maybe some more general questions. Regarding the first ones, I would like to ask if you can better specify the difference between energy management system and power management system, since you mentioned both models.
Yes, energy management system and power management system is a subject that funnily comes around very often, and and we often find the contradictory versions. But in a general sense, energy management system is the system that is in charge of scheduling and foresee the functioning, what we want the system to behave. And power management system in this case is what we talk of the system that manages the real-time operation of the power center. So if for example the forecast was foreseen, the forecast was X value and the real production is Y. In that case, it's the power management system who will have the embedded logic and the models to take the better solution and adapt to this situation. The energy management system, it only foresees I want you to achieve this point because it's the best for us. And the power management system is in charge of, okay, I hear you and I'm gonna do my best to achieve that. I don't know if that's
Yeah, so when you speak about the power management system, maybe you mean also something related to the control, maybe also to the real-time control of production and consumption.
Exactly. In our case, for example, the energy management system in these sites is installed in a server. It's a server, the server that is located on sites, and the power management system, the logic and its operations are embedded in the PLC and the programmable logic controller that is on site, which reacts very fast and also has some other occupations in terms of safety and electrical configurations.
Yes, another question regarding the models you presented in the energy management system. I saw that you consider different constraints regarding active power. I would like to know if you think that it could be also interesting to consider reactive power management, and if yes, which are the best benefits to include also reactive power modeling?
Yes, actually, reactive power wasn't treated because of how this the objective capacity firming framework focused primarily on active power, and because also this notion was predetermined by the grid manager, given that all the sites in that follow this constraint, this capacity firming framework, they have to obey a law that they call the reactive power law. So given a certain production and a measurement of grid tension, you are supposed to be able to furnish some part of an ancillary service of voltage control. So the sites they do adhere to, they do have some reactive power logic that is included, and we could include this this part of the power control on optimization problems. But given that it is very dependent on the current scenario of the site, and it is mostly done to through the power electronics of the VSS, it has a very small impact on the normal operation of the energy storage. However, it could be interesting, however, to see if there is a limit in which that starts being the case, and the reactive power starts to influence maybe the lifespan of the power conversion system of the VSS.
Also, maybe to model, I don't know, capability curves to see how the working point of battery changes as a function of time, maybe with different operating conditions. Another specific question is related to the energy management system. I would like to know if you can provide some information, some data regarding the computational time of your model.
Yes, the model actually developed on the energy management system that is deployed on site. It takes, if generally speaking, today it takes between 1 and 2 seconds to generate the power profile. It, however, does not include the thermal dependency. And when we saw that we included the thermal dependency and the co-estimation, given that it is a nonlinear phenomena, in that case, we saw the time to increase drastically to 15 minutes, 20 minutes. So we saw an increase, but in the energy management system, the process today is fairly quick. And furthermore, because the models are already parameterized, we parameterize it in different systems, and we just introduce the newer parameters on the model used for the scheduling.
Do you think it could be possible to linearize the model, or maybe by linearizing the model, you will lose the correct description of the physical operation of batteries?
Yes, by linearizing the thermal model, we're going to lose some precision. So given that the impact today is of the thermal dependence is weak, we did not consider that, but however, we could explore this task in the future, which is part of what Madame Brie also said regarding the thermal model and how to simplify it.
Okay, so now I have only a final general question regarding more the topic of variability of RES, renewable sources production. You have developed a very deep analysis of the state of the art of the technologies used in this domain. I would like to know what do you think is the best way to mitigate the variability of renewable power plants today?
The best way to mitigate today, given that I work on batteries, I'm going to say batteries. But in a more serious note, to mitigate the variability, if we remain on a small scale, I think that local consumption control can be very of a lot of interest to mitigate the variability. On a large scale, photovoltaic aggregation can really solve this problem without the need of can reduce this problem without the needs of energy storage systems, and in that case we can reduce this variability and have something that is more more easy to manage in the grid. But in my opinion, it is the flexibility that offers us an energy storage system, even if the capacity is small with a high power, is something that can really mitigate a lot of the intermittency on short term.
Okay, for me it's enough. Thank you so much for your answers.
Thank you.
Thank you both for the answers and the questions. So the next examiner is Dr. Theodoros Kalogiannis from Brussels. Please take the floor.
Hello, can you hear me?
Yes.
Yes.
Hello. Thank you for the nice introduction, and thank you, Alberto, for the nice presentation and your work you have performed. It is quite significant, and I would like to highlight the originality that explores and contributes to the recent needs in energy storage. So congrats so far for your work and your presentation. I would like to have the first question following what Stefan already asked about the support of the renewable energies. I have seen your passion for the batteries, and I can say that I'm also working in the battery field and I have the same passion. But why and how these solutions were selected in the end? Have you also investigated other type of energy storage that they can have maybe low capacity but high power capabilities, or it was explicitly targeted to lithium-ion batteries?
The storage solutions that were deployed on sites?
Yes.
Yes. So the storage solutions that were deployed on sites were of this kind, mostly because there was they were not. Let's start by openly say they were not chosen by us specifically. We just invited the developer to use them, and the reason because of that was because the energy system that was to be deployed to the EMS and the PMS that were to be deployed at the moment of the case of study. The case of project development, there wasn't still a lot of feedback and how to properly manage and control these systems. And what we found is that this kind of solutions, lithium-based and the chosen, allowed the flexibility and the control requirements that were needed for the system. So it was very focused on the power control capabilities that these systems have.
Okay, so did you also explore some other type of solutions, or you started your research by taking in the lithium-ion batteries as the application to use with?
No, we did not explore the usage of other batteries, given that this technical solution was already foreseen. We started directly based on this kind of solutions, but the evaluation of other kind of energy storage technologies was not explicitly considered.
Okay, and these batteries that you're using are coming from already first life, they are at their second life, or they are new, brand new, and they are starting their application?
Yeah, these were batteries that they started their application. They were not second life batteries. They were brand new at the beginning of the life of the projects.
Okay, thanks. Then I will go more into some technical questions, and I would like to ask you something about the figures that we have here. I keep noticing this warranty curve, the green curve, and
Yes.
I can't understand and why there are some slopes in the curve of the manufacturer why after 1000 cycles the lifetime is decreasing faster, then it is not increasing so fast, and then we have no aging? How to explain this?
Yes, we noticed that the warranty of the manufacturer was furnished, was proposed in this way. We asked, and they told us only that it was related to the fact that during the initial period of life of the energy system, they were more reassured of the behavior it's going to have, and afterwards, the more time passes, as they are less sure or less, there's more probability of a smaller capacity of smaller failures. It's a big word, but small failures on the cells, and they kind of do this to give themselves more headroom and avoid find themselves on an overpromised capacity.
To be honest, I would expect the opposite, to have like a higher window of safety in the beginning of life, and then the slope to become more steep in the ending of life.
Yes, it's because battery cell degradation usually is very steep at the beginning, and then it stabilizes. In this case, they chose a different approach to the manufacturer. I'm not really sure the specific reason other than that they communicated me at the time, but actually something that is very interesting, and I can inquire more about later.
Okay, but this is not a pattern that you have followed in your prediction. So I saw, if I'm not mistaken, that a more steady slope, it is predicted from your models, right?
I did not understand the question, sorry.
So the model of your capacity degradation is more steady with a constant rate of change. It doesn't have these changes.
Yes, our model is more constant. Is a more standard behavior of degradation that is expected from batteries, in which there's the initial strong degradation due to the first SAA layer formations, and then just the cyclical degradation. But yes, our system is more soft and does not degrade radically. But as I said, that is probably linked to the fact that the manufacturer does not want to put itself at risk of having to pay extra O&M operations and maintenance interventions. Sorry.
And about this SCI layer, why you selected that the degradation mode, it is the SCI? Have you opened the batteries to validate your assumption, or this is something based on your expertise? And
no, we have not. We cannot open the BSS that are deployed. So it was just mostly based, given that the degradation that we observed on the system and the report on the literature relies heavily and is on this SA formation, this fast degradation. We included a parameter for it to account this behavior, but we do not have a first-hand experimental data about that.
okay, can you go please to slide 23? Yeah, I have some question about the model. So this is the temperature that it is validated over the period of 3 times. Did you also incorporate the aging model to predict the temperature over lifetime?
On the lifetime, no, we did not explore the temperature model on the lifetime of the battery. We just evaluated the temperature and the estimation that we can have on a continuous day operation. But no, the lifetime was not evaluated. Although we can indeed we we can try to explore this increase on of degradation due to temperature on the lifetime of the system can be something that that could be of interest to.
Yeah, I think it could be a nice parameter to include, because I see that you have an internal resistance of some 100 nano-ohms. This is the internal resistance of the battery or of the module, or how do you define this internal resistance?
Yes,
Okay.
this is internal. It's not on these batteries. We did not have laboratory measurements, and we did not have any experimental data. So this internal resistance is the internal resistance of the thermal model for the heat generation, and what we do is we determine it through the parameterization of the system, but there is no measurement of the internal resistance to determine. Yeah.
But do you know where the temperature reading is coming from? The one that you have with the blue curve. Is it on the battery cell? Is it on the module? Or it is unknown and it is just the reading of the whole battery module?
These cells on these batteries were located in the center of the battery pack, on the battery system. But however, the model is agnostic to that, in the sense that it considers that we consider that if the temperature is given by the BSS, it is a temperature that has significance itself for the safety of the system.
Yeah, and what is the, okay, maybe I will not ask this, but regarding the dimensions and the volume of the module, you can have, localized temperature increase or uniformities among the battery pack. So perhaps considering multiple temperature sensors would improve your model. Averaging the temperature points will also give you some significant values, just for future reference.
Yes.
Okay.
Thank you.
I have some, I have some question about optimization. So you didn't include the thermal model or the aging model in the optimization.
No, the aging model is not considered itself in the optimization. It's something that we evaluate afterwards, given the optimal usage of the battery. We determine what is the degradation linked to that optimal usage. In regarding to the thermal dependence, we included the model in the capacity firming framework, and we also saw the increase of the reduction in this case of expected revenue by inclusion. But we saw also that it was not as significant as expected. But in any case, the usage of the degradation into the optimization problem is indeed something that we can identify as a potential work for to develop this degradation aware optimization framework of the BSS.
And regarding this optimization, did you consider any carbon footprint because you're using renewable energy storage? It was somehow incorporated, or are you planning to incorporate this in your equations, like reducing the CO2 emissions? And on the other hand, why you are not using some more conventional, let's say, power production or energy storage?
Currently these optimizations were really tailored to this capacity firming scenario. So we did not actually explore the addition of other terms of interest. but there's something. Indeed, this is something that we can foresee to add more parameters to add some value or more value to the optimization framework.
Yeah, it is just a suggestion, because when using the battery cells, usually we can expect a lifetime of 10 years, but we don't know if this is going to compensate the CO2 that the carbon footprint that they produce together with the application. Okay.
Yeah. Yes.
I don't have other questions for your presentation. I think we can summarize it here. Thank you again for your work, and good luck with your future challenges.
Thank you.
Okay, thank you both of you. So we have two examiners more. The first one is Andrea Michiori, so you can just continue with the questions. Michiori, sorry.
Here, I think there's Andrea who would like to. I don't know how to turn it on.
Oh, it works.
So you are in
thank you,
person.
Alberto.
You are there in person, okay.
Yes, sorry.
I think that I will be fast anyway. Actually, I wanted to ask you exactly this question, or a question about this slide. We discussed also about this before. This model, okay, it looks that there's a little error, but somehow it doesn't manage to capture really some event. And at a certain point we say, okay, what is missing actually is some part of the measurement. What do you have if by chance you had the possibility to think a little more about this, or you had more information? What do you think is actually missing in the inputs of this model, or anyway in the model itself, in order to cover well, to reduce that problem of the behavior?
Yes, to solve this missing data, what I think is missing is really the heat related to the chemical reaction inside. So I think that will add some nice complexity to the model to be able to reproduce more accurately its behavior. And by doing that, I think that we will have a more closer minute to minute or instant to instant temperature estimation. But that's
Okay. Thank you. And I'll pass it to George then. No, not yet. So it's all for me.
So you finished, okay. So before I give the podium to mentor, I will just raise some questions as a member of this committee as examiner. So if you go to the slides somewhere at the beginning where you're presenting capacity for forming, the definition, there are some solar production. This one, yes. So we can see here that we're talking about 1 day. So we have to make our forecast for the next day, if I understand correctly.
Yes. In this capacity, the 2015
Yes.
capacity firming framework of
Okay.
for the island Corsica, it was a requirement.
Yeah, and there is on page 10 and 36, you are talking about long-term management. So my question is, do we really need a long-term management in this problem, since we are talking about capacity firming where the next day is considered, the next 24 hours, which is short-term. So where do you use your long-term management? Because obviously it's not used in the capacity firming, if I understand correctly. You can make some comments on this.
Yes, indeed. On the daily to-day operation, there is no notion of long term. In the long term management comes when we start to evaluate the capacity degradation from that is expected on the optimal operation throughout the life of the sites. So at the beginning, given the operation of the system and the warranty and the manufacturer that we can foresee a 10-year scenario. However, when we start to include our models and into this capacity framework and the optimization scenario, we can, in that case, start to see that the expected degradation is less or more, and therefore we can also start to adapt our behavior to that.
Okay, thank you. What about, okay, here we are using the battery for the capacity firming. What about usage the battery for voltage control? Because we know that our photovoltaic power plants can also increase the voltage at some point in the system. So did you think about this one also or not?
For voltage control, this capacity firming framework, we did not look at it with this optic. The capacity, the specific capacity framework we did does have some voltage control, and it has a voltage regulation to law to adapt to the grid viability, but it's not something that was focused in this work to include this voltage control.
Yeah. Okay, so next one, you were using Python, if I understand, and you were using the toolbox, or let's say solvers that are already included in Python. But I'm missing maybe some description of the methodology for optimization. Which method did you use for optimization?
Which method we use for optimization? Which toolbox?
For optimization, yes.
I'm blanking on the name of the toolbox. I'm really blanking on the name, but
I'm not asking about the name of the toolbox and the solver because you already mentioned this in your thesis. But just the question is, which method optimization did you use? Is it linear programming? Is it non-linear programming, or some?
Yes, it was. At the end, what we used was a mixed integer nonlinear programming method that we used to solve it. When we incorporated the thermal component that is nonlinear, and given that some constraints are binary, at the end it was a min LP problem that we faced.
Okay. So that was the question, because already other members of committee were asking about linearization and non-linear problems and so on. So that's why I was asking the same question. Let me check if I have some other questions.
Sorry.
Okay, that's all from my side because you already answered all the questions. Thank you, and congratulations for your work and presentation. And now I will just leave the podium to your mentor for some questions, comments, please.
Thank you very much, Mr. President.
Yes.
I don't.
Now it should be okay. Thank you. Thanks, Mr. President. So from my side, maybe I have one question that was not clear at the end, at the last slide, when you have the three models and you speak about joint optimization, the possibility to identify the parameters of each model separately or jointly, but it was not clear if at the end you did the joint identification or not.
Yes,
and what is the challenge related to this?
Yes, I must have misspoke. Indeed, when I talk about joint, no, we parameterize each model individually, and then when we want to apply it onto the EMS and PMS on site, is where we do co-estimation, and we show the interdependency between them. But there was at least in this work done, there was not an approach to co-parameterize the models.
To estimate simultaneously the parameters of the three models.
Yes, now do
you think if you do this, there will be a difference or not? I mean, would that maybe explain the mismatch you showed at the curve at the slide that was discussed before by Andrea? Or?
I think that by doing an approach like that, we can find ourselves in the case in which the model itself will be maybe less precise, given that when we co-estimate all the values at the same time, we're gonna lose some insight. No, I think I'm mixing myself in my head. But if we co-estimate both the three systems at the time, I think we can have maybe something that is very just for the data that we have, but I'm afraid that we will maybe overfit the solution and it will lose the general applicability that we could have to integrate it into other systems.
Okay, so that is the question I had. Otherwise, I don't have any other question. I would like to thank for this work, and also to thank the industrial partner who supported this work, actually, because the added value comes to a high degree from the real data that are difficult to have today in this kind of research to estimate parameters of the models. Usually the works are done in laboratory. Of course, we have more and more such data available, but we have to face challenges like the confidentiality of the manufacturers, that they do not give very detailed access to the inside the system. So we have to estimate the physical object, which is very complex, the battery, using the few parameters that are observable, actually, the few values that are observable. Anyway, I would like also to make a reference to my colleague who was at the beginning of this PhD, François Nirac, who passed away in the meantime and could not be here today. Thanks, and I pass back the floor to the president.
Okay, thank you. Yes, I agree. The support from the industry is very important. I think this is another level of this PhD thesis. Without this, it would be only theoretical, but now it's completely industrial and industrial based, and that's good. This is the big advantage. Since we have some audience present, I would like to ask, does someone from the audience holding the PhD have any questions for our candidate or not?
Well, from the audience here, it is not the case.
Yes.
Okay. I thought that there are some people there in the room. If not, I think we can conclude this part of this process today, and the committee now will move to another room. So the candidate, please wait for our last decision. So we'll be back in a couple of minutes.
Okay. See you at the other link in a few minutes. Thank you.
Yes.
Thank you.
Bye.
C'est vrai que la personne m'a posé la question sur un type de problème d'optimisation. C'est vrai que j'en parle pas trop parce que c'est quelque chose parce que ça parle pas trop. J'attendais pas la question non plus. Ah oui, bon, c'est bon, c'est vrai que c'est un peu. C'est pour la question. Oui, ils sont deux, nous aussi. Non, mais attends, c'est pas plus compliqué que ça. Ouais, non, c'est vraiment. Moi, le mec. C'est ça, il a essayé un modèle, il a essayé sans batterie. C'est ça, il a non, c'est vrai que ça semble. C'est vrai que ça semble contre-intuitif parce que normalement, les constructeurs de batteries. Non, 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 bah, il va tenir très longtemps. Et toi, ce que tu vois avec tes batteries, la version tout ça, c'est que c'est toujours pire que ça qui te va bien. Mais là, comme il s'engage financièrement, là, c'est pas la même histoire. Et ça, c'est. Après, c'est parce que moi aussi, j'ai fait un peu exprès de ne pas parler de ça dans les manuscrits. Je pense qu'ils ont dû comprendre. Je n'ai pas dit exactement tellement. C'est le premier chapitre que j'ai fait, du coup, ça date depuis. C'est intéressant. Il y a quelques questions que j'aurais bien aimé mieux. Ouais, surtout que moi, j'ai fait ça exprès en médecine qui est. Ça pourrait être sympa si vous l'avez fait en français, s'il y avait un truc qui est écrit.
You are in the meeting now.
Normalement, on peut résoudre ça. Ah, dans le sens. Sinon, je pense avec lui. Oui, il y en a deux.
Okay, so now we have all the jury connected back, and I let the floor to the president.
Thank you. The candidate is also here.
Yes.
Okay.
Yes.
Okay. So I will just read the report of our jury, and then we will proceed with the procedure. So Mr. Alberto Eric VAZQUEZ Rodriguez defended his thesis entitled Advanced Modeling and Techno-Economic Optimization of Operation Strategies of Electrochemical Storage Systems, Accounting for Cycling Constraints. He made a clear and synthetic presentation of his work. The presentation was of good quality and easy to follow and showed his pedagogical skill. The context of the performed research was very complex. From the industry point of view, he was capable to justify the assumptions made in the thesis. He managed to provide very good and fair answers that went even beyond the scope of the thesis. He was able to elaborate on his work to highlight his contribution in the field. Furthermore, he showed a good mastery of the subject, both on the experimental aspect and on the simulation and modeling aspects. The perspectives of his work are rich and important for future applications in photovoltaic and storage industrial sectors. In conclusion, the jury agrees that the work brings original contributions, is well presented, and of value to both the scientific community and the relevant industry. Therefore, the jury unanimously decided to award Mr. Alberto Eric VAZQUEZ Rodriguez the grade of Doctor in Energy and Processes of Paris Science and Letters University, prepared by Mines Paris in the frame of the doctoral school number 2621. Engineered the systems, and okay, I can't read this in French, but yes, it's the doctoral school number 2621. Thank you. Congratulations to our candidate.
Congratulations, Alberto. And now, thank you to the president for the announcement of the result. So now the next step is to pronounce the oath.
Hello? Yes. Okay. In the presence of my peers, with the completion of my doctorate in energy and process engineering, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, to my methods, and to my results.
Congratulations, Alberto.
Thank you very much. Well, I wanted to thank you all and for coming today and supporting me, and also to visualizing my presentation on PhD defense. I want to particularly thank George, because he has really helped me through this process and in these particular conditions that happen in this thesis, and the sadness that we faced. And we arrived at the objective, and so thank you very much. And thanks, Andrea, because you also helped me a lot in this process. You brought me really guidance in several moments, and you really brought me a new different perspective on several points. And I really want to thank you because of that. And at last, well, I want to thank my enterprise, who also allowed me and gave me a vote of confidence and allowed me to finish this process. And it goes without saying also my family. I thank them a lot, because it is because of them that I'm here, and my girlfriend. And thank you very much. And that's it. Thank you. Yes, and also yes. Sorry, I would also like to thank the jury and the president of the jury for their help. I'm so sorry, and their questions were very interesting. They really helped me to gain a perspective and future subjects that we can treat on future works, and to apply either on this industrial or on other research. So I thought the interactions I had with them and the feedback we got from them was really interesting, and it can really lead us to some more interesting results and research. So thank you very much.
Okay. Thanks from our side also to all the members of the jury again, and we hope to have an occasion soon to see you in person at some other event. And here I think we can close the process. Thank you.
Okay, thank you. Good luck.
Thank you very much.
Thank you very much.
Bye.
Bye-bye.
Bye-bye.